Hello and welcome back. Today we'll be doing question 2 from the 2005 Step Paper 2. So, let's get started. Question 2. For any positive integer n, the function f of n is defined by f of n equals n multiplied by 1 minus 1 over p1 multiplied by 1 minus 1 over p2 all the way to 1 minus 1 over pk, where p1, p2, all the way to pk are the only prime numbers that are factors of n. Thus, f of 80 is 80, 1 minus 1 half, 1 minus 1 fifth. Part A, Part 1. Evaluate f of 12 and f of 180. Part 2. Show that f of n is an integer for all n. Part B. Prove or disprove by means of a counterexample each of the following. 1. F of n is equal to f of mn. Part 2. F of p, f of q equals f of pq if p and q are distinct prime numbers. 3. F of p, f of q equals f of pq only if p and q are distinct prime numbers. C. Find a positive integer m and a prime number p such that f of p to the m is 146410. Pause the video to have a think, and once you're ready, restart to see if you were correct. So let's get started with A part 1. So we'll notice that 12 can be factorised as 2 squared times 3, and so 2 and 3 are its only prime number factors. Therefore, we have f of 12 is 12 multiplied by 1 minus 1 half multiplied by 1 minus 1 third, which is 4. Now, we'll do 180. This is 2 squared times 3 squared times 5. So 2, 3, and 5 are its only prime number factors. F of 180 is therefore 180 times 1 minus 1 half times 1 minus 1 third times 1 minus 1 fifth, which is 52. Now we'll move on to part 2. Firstly, we can rewrite the expression for f of n like so. Then we can take all the denominators out of our fractions and put them underneath our n to leave a string of integers on the right here. Now, the left-hand side here is an integer, because p1, p2, all the way to pk is guaranteed to be a factor of n, and therefore f of n is always an integer. Now let's move on to part B. So firstly, for part 1 here, a good counterexample is m equals 4, n equals 6. If you evaluate f of 4 and f of 6, you get 4, but if you evaluate f of 24, you get 8. Now, we'll move on to part 2. This one here is actually true. So, we can prove this by noticing that the only prime number factor of p is p, and the only prime number factor of q is q. Therefore, the expression simplifies to p minus 1, q minus 1. Similarly, there are only 2 prime number factors of pq, p and q. Therefore, their expression becomes pq, 1 minus 1 over p, 1 minus 1 over q. This, of course, simplifies to the exact same as the one above. Now, for part 3, we have a counterexample here. P equals 4 and Q equals 3. This shows that even if they are equal, one of them can be a composite number. Now, we'll finally move on to part 3. So, here we'll notice that p to the m will only have p as a prime number factor. So f of p to the m is p to the m 1 minus 1 over p. This can simplify to p to the m minus 1 of p minus 1 equals 146410. Now this looks a bit like a row from Pascal's triangle over here, which implies that this here is a power of 11. Additionally, if p is 11, then p minus 1 is 10, which explains the 0 at the end here. Therefore, we have p equals 11 and m minus 1 equals 4, which satisfies the requirements, and therefore m is 5. And that's my answer. If you liked our video, please like and subscribe, and we'll see you next time for some more fun maths problems. Thanks for watching, and goodbye.